The topic of this lecture is Important Theorems, Part 1 of Improper Integral. We'll cover these points in this lecture: test for convergence, positive integrands, theorem number 1, theorem number 2, theorem number 3, comparison test, and theorem number 4, comparison test, limit form. So let us see first theorem. What are the important points? Let A be the only point of infinite discontinuity of a function f, which is integrable on closed interval a plus epsilon to b for all epsilon satisfying this inequality, and fx is greater than 0 for all x belongs to ab. If these are the assumptions, then a necessary and sufficient condition for convergence of improper integral a to b fx dx is that there exists a positive real number k such that a plus epsilon to b integration fx dx is less than k for all epsilon satisfying this inequality. So if this condition holds, then the necessary and condition and sufficient condition is this, that improper integral a to b fx dx is convergent if this expression is less than k for all epsilon satisfying this. So proof is very easy. We'll start with phi epsilon is equal to integration a to b, a plus epsilon to b fx dx. And recall, if limit epsilon tends to 0, phi epsilon gets finite value, then we say this improper integral is convergent. So let us see how to proceed. We'll take two values, epsilon 1 and epsilon 2, where 0 less than epsilon 1 less than epsilon 2 less than b minus a, and we calculate phi epsilon 1 minus phi epsilon 2. This is nothing but integration a plus epsilon 1 to a plus epsilon 2 fx dx, and this is greater than equal to 0. Why? Because fx is greater than equal to 0 on a plus epsilon 1 to a plus epsilon 2 because of these assumptions. Now, since 0 less than epsilon 1 less than epsilon 2, it follows that phi epsilon 1 is greater than equal to phi epsilon 2 because of this. So this shows that phi is monotonic decreasing function on this interval, because epsilon 1 is less than epsilon 2 and we are getting phi epsilon 1 is greater than phi epsilon 2. Therefore, phi epsilon will tends to a finite limit as epsilon tends to 0 plus if and only if phi is bounded above. Now, what does it mean by phi is bounded above? Phi is defined by this. So phi is bounded above means there exists a real number k such that this integration a plus epsilon to b fx dx is less than k for all epsilon satisfying this quantity, and k is positive real number. So by this way, we have proved the necessary and sufficient condition for convergence of improper integral this. Note that if phi is not bounded above, then phi epsilon tends to infinity as epsilon tends to 0 plus, and the improper integral is divergent in this case. Now let us see the theorem number 2. Here the proof is similar to that the previous theorem. Here in place of a, b is the only point of infinite discontinuity and all assumptions are same, and f is integrable on, in place of a plus epsilon to b, here it is integrable on a to b minus epsilon. So the necessary and sufficient condition is this, that there exists a positive real number k such that integration a to b minus epsilon fx dx is less than k for all epsilon satisfying this. So proof is very similar. You can try it. It's very easy. Now let us proceed to theorem number 3, that is comparison test. What are the assumptions? Again, the let a is the only point of infinite discontinuity of functions f and g. So here two functions are involved, where and both are integrable on a plus epsilon to b, that is from a to a plus epsilon to b, these functions are not having any problem in the sense that they are integrable on this interval. And there is a one more condition that for all x belongs to open interval a close interval b, we have 0 is less than fx less than equal to k times gx, where k is greater than 0. So these are the assumptions. If this happens, then integration a to b gx dx is convergent, then integration a to b fx dx is convergent, and if a to b fx dx is divergent, then a to b gx dx is divergent. Note that this fx is dominated, in some sense fx is dominated by k times gx, that is fx is dominated by gx in this case. So let us see the proof. Since f and g both are integrable on a plus epsilon to b, and 0 less than fx less than or equal to k times gx, so we have a plus epsilon to b fx dx is less than equal to k times a plus epsilon to b gx dx holds. That is, if this relation holds over here, this relation holds over here also in case of integration. This holds for all epsilon satisfying this. Now let us see case 1. If a to b gx dx is convergent, then there exists a positive real number k dash such that a plus epsilon to b gx dx is less than equal to k dash, because of the previous theorem. For all epsilon satisfying this lies in 0 to b minus a. Thus, a to a plus epsilon to b fx dx will be less than equal to k times k dash. That is, this expression is less than some constant for all epsilons lying in this interval. Therefore, using the previous theorem, we can say this integration a to b fx dx is convergent. So this first part we have proved. Now let us see the second part. Now let us see the case number 2. We define phi epsilon by this expression a plus epsilon to b fx dx and psi epsilon by a plus epsilon to b gx dx, or all epsilons lying in this interval. Then since phi epsilon is less than k times psi epsilon, why this is so? Because we are having this relation a plus epsilon to b fx dx is less than equal to k times a plus epsilon to b gx dx. So because of this relation, if fx a to b fx dx is divergent, then phi epsilon is not bounded above, because this is fx dx is divergent, so phi epsilon is not bounded above. Now if it is not bounded above, then psi epsilon is also not bounded above on open interval 0 to b minus a. But what this implies? This implies that a to b gx dx is divergent, because if this is convergent, then psi epsilon, this should also bounded using the previous theorem, but it is not bounded, so we declare that a to b gx dx is divergent. Remark, if psi epsilon is bounded, suppose if psi epsilon is bounded, then phi epsilon will also bounded because of this relation. On this implies that a to b fx dx is convergent, but we have assumed that a to b fx dx is divergent. So because of this, phi epsilon is not bounded implies psi epsilon is not bounded. So we have proved this. This is the extra things remark. This is the explanation why phi epsilon is not bounded, then psi epsilon is also not bounded. So let us proceed for the next theorem. This is the comparison test limit form. Let us see what are the assumptions over here. Let A is the only point of infinite discontinuity of function f and g, and both are integrable on this interval a plus epsilon to b. And for epsilon satisfies then its inequality, and fx is greater than 0, gx is greater than 0. These two are assumption for all x belongs to open interval a to close interval b. Now if limit x tends to a plus fx by gx is L, where L is non-zero finite number. This is important. L is non-zero finite number. Then the two improper integral a to b fx dx and a to b gx dx both converges or diverges together. That is, if all these assumptions are satisfied and if this limit is a non-zero finite number, then these two improper integral behave similarly. That is, both are diverges or both are converges together. So let us see the proof. The proof is very easy. Since fx by gx is greater than 0 because of our assumptions that both are greater than 0, or all x belongs to open interval a to close interval b, and L is non-zero, we have L is greater than 0 because L is the limit of fx by gx, and it is because this expression is greater than 0 and L is non-zero, so L is greater than 0. So we can select an epsilon greater than 0 such that L minus epsilon is greater than 0. Suppose somewhere is 0 here, L is non-zero, greater than 0 quantity. So we can find epsilon such that L minus epsilon is also greater than 0. Now since limit x tends to a fx by gx is L, so there exists a point C. We can find a point C because of using the definition of limit. We can find a point C such that L minus epsilon is less than fx by gx is less than L plus epsilon for all x belongs to a plus b. Using the definition of limit, we can easily find a value C for which this holds. Now what we can do, we can multiply gx on both sides and we get the inequality L minus epsilon gx is less than fx less than L plus epsilon. Note that this L minus epsilon and L plus epsilon are positive number, so these two will not create any problem when we'll proceed. So now let us see the case number 1. If a to b fx dx is convergent, let us suppose this, then a to c fx dx is also convergent. And since L minus epsilon gx is less than fx, that is gx is dominated by 1 upon L minus epsilon fx, or this expression is dominated by fx, we can say, and L minus epsilon is greater than 0. So by comparison test, if a to c gx dx is also convergent, because in some sense gx is dominated by fx and fx integration a to c fx dx is convergent, so a to c gx dx is also convergent. So this implies that integration a to b dx is also convergent. Now let us see the case number 2. Here let a to b gx dx is convergent. If this convergent, then a to c gx dx is also convergent, and using this part fx is less than equal to L plus epsilon gx for all x belongs to S to C, and L plus epsilon is greater than 0. So again, using comparison test, we can say that a to c fx dx is convergent, and when a to c fx dx is convergent, so this implies a to b fx dx is also convergent. Now let us see the case number 3. If a to b fx dx is divergent, then a to c fx dx is also divergent. And since L plus epsilon gx is greater than fx, that is, we are using this part now. So if fx is a to b fx dx is divergent, and this quantity L plus epsilon gx is greater than fx, so in some sense and L plus epsilon is greater than 0. So by again the comparison test, we say a to c gx dx is divergent. That is, this implies a to b gx dx is also divergent. Now let us see the fourth case. Let a to b gx dx is divergent. then a to c gx dx is divergent, and using the previous inequality, this inequality, we can see since fx is greater than 1 plus delta, it is written delta but it should be epsilon, fx greater than 0, fx is greater than or equal to 1 minus epsilon gx for all x belongs to a to c, and 1 minus epsilon is greater than 0. So a to b fx dx is divergent by comparison test. Therefore, a to b fx dx is also divergent. Thus, the improper integral a to b fx dx and improper integral a to b gx dx both either converges or diverges together. Thank you very much. You can find the this PDF in the description box.